Mwah! Ah. Hi, everybody. I spy a Pyrex. Whoa. Let's see, I've got captions. They're doing the caption thing. Yes. Yes, we have things. And/or stuff. Stuff and/or things. I'm sure it's fine. I'll be doing this evening. Gonna do some more stuff. I am so stoked. Wait, did I save this? I saved the sticky note. Okay, good. Okay. All right, I'm gonna grab that. So we're continuing more of the 30 Days Lost in Space series. And it's a tiny bit of a recap because this does pick up from where we left off. We decrypted a key. We took code that was Caesar shifted, which makes me immediately think of a Le Brutus joke. But yeah, no, that's fine. This isn't history class. Wrong pivot. We converted the code back into something we could run with a shift 19. And then we ran it, and we got three numbers. We got 23, 353, and 1688. So I did not look at the example for this week. So we're both going into this very much blind, and just seeing what we're doing next. I'm stoked. I've also been researching, because I know when we get through the exercises in this, I know I'm going to want to do more because this is a bunch of fun. I've been debating a project, so don't have anything just yet for you, but the cogs are turning at the moment. I'm very excited. Ooh, you've been playing with electronics yourself. ESP8266. Ooh, fancy, very fancy. Very exciting. Hi, Pyro. A bow. Yes. So we're gonna do stuff and things. Let me get us going here. So I did look into my tracking. It just does that now with the sensor, so I'm probably gonna end up having to replace it. Some tracking is better than no tracking. For whatever reason, the software will just casually take my other arm and stick it on my face. I've looked at the debugging for it. It just does that. I don't know why. I'm chalking it up to the sensor being a little twitchy. Yeah, it works for the most part until it doesn't. But naturally, yeah, be what it is. It's fine when both of my hands are in frame. It's when this hand goes out of frame, like if I purposely put my arm down and I move my head around, it picks the arm back up for whatever reason. Now it won't do it, of course. Erg. So yeah, nah, it be what it is. Don't get too excited. It don't work yet. Come on, Parks. Like that's part of the experience, is not having any idea what you're doing, and then by the end of it, you hopefully have something cool that you can say you did. That's literally what I'm doing here. I have been so stoked to do this stuff in the evening because of the fact that I know how a resistor works, I know how an LED works, I know how a rectifier functions, but to actually take these individual components and do something with them, read things and like toy with actual microcontrollers. I hadn't done a whole lot of that before this. It's just super fun experience. You get to cook up all sorts of fun things. So with that, we are gonna hop right into our stuff and things here. So let me take a moment here. We're gonna put the brakes on that, and we'll put the brakes on that. Yeah, the onboard LED. Let's go. Oh, that's exciting. Oh, congratulations. It's awesome. It's awesome to get that first little tidbit to just do stuff. Okay. We have our stuff. Let's see where this goes. I don't know how much of this I'm going to let play. I guess I might let the instructor talk while my hand spazzes. Hi, Jazz. Why are my commands not working? Oh, bugger.
Ah, there you are, Explorer. Welcome to day 18 of our fantastic interstellar adventure. I hope you're well rested and ready to embark on today's journey. Great work on the last mission, Sherlock. You've got the brains, but now we're gonna need the brawn. Your keypad worked fine for real-time input into the hero, but we'll need precise thrust control for our ascent rate to the surface without risking any, let's say, unplanned rapid disassembly. Or we could run straight into Rachel. Same thing.
Wait, what?
Game over.
Wait, what? Oh.
Fortunately, the hero kit contains just the sensor we need for subtle or forceful control. A rotary encoder. All right, let's dive into today's hardware discussion. Our star of the day is the rotary encoder. But what exactly is it? In simple terms, a rotary encoder sends direction of rotation signals and the amount of turn. It can also send an on or off signal with a push. Pick it up and play with it. Every click you feel as you turn the encoder is counted, and the direction you're turning it is noted. These two pieces of information are sent to our board as a sequence of high and low signals. The rotary encoder is particularly useful for scrolling through menus, adjusting variables on the fly, and in our case, delicately controlling our ascent rate. Moving on. It's time for some nerdy distinctions. There are two types of encoders, absolute and relative. An absolute encoder has a unique value for every specific angular position of the knob. There's a maximum clockwise position and a maximum counterclockwise position. You know precisely where you are at all times. A relative encoder, on the other hand, like the one we're using today, can turn endlessly.
Yay!
It doesn't have an end, so to speak. It tells you how far and in which direction the knob has been turned from its starting position. But it doesn't give you a specific location.
I don't need it.
Our relative encoder has 20 distinct clicks for a complete 360-degree rotation.
Okay.
That means each click corresponds to an 18-degree rotation. That's our encoder's angular resolution. Now that we have a good understanding of our new component, let's talk about how we're going to hook it up to our control panel. We connect the 5V to the plus symbol, or VCC terminal, and ground to the GND terminal. CLK, or A, and DT, or B, are the clever bits. They help us figure out which way the knob is being turned. There's also an SW terminal. That's for the push switch built into the encoder. Push down on the knob, and it acts like a button. Neat, huh? But we won't be using that feature in our project today. I think it's time we move on to the code. Wouldn't you agree?
No.
Right. Let's get a bit technical now. This rotating encoder gadget is all about timing. We want to know two things. One, the direction of rotation, and two, the rate of rotation. The direction of the rotation is rather straightforward. When the knob starts turning, one of our two signals, CLK or A, and DT or B, will get excited and go high before the other. Which one goes first tells us the direction of rotation. Essentially, if our CLK signal gets all giddy and turns high before our DT signal, we know the rotary encoder is spinning clockwise, like the hands on a traditional clock. If, on the other hand, our DT signal jumps the gun and goes high before CLK, we know the rotary encoder is spinning counterclockwise. Isn't that just a slice of fried gold? The rate of rotation is a bit more complex. I think we'll save that juicy bit for later. For now, let's make sure we get that direction detection working perfectly. Right, so we know that the order in which our signals go high determines the direction of rotation. But how do we accurately and efficiently detect that?
Good question.
Enter our secret weapon, the interrupt.
Neat.
An interrupt is a rather brilliant feature in microcontrollers that says, "Hey, listen! Something important just happened. Stop what you're doing and pay attention to this right now." This allows us to interrupt the normal flow of our code to react to a specific event. In our case, when either CLK or DT goes from high to low or from low to high. Or, in simple words, when either CLK or DT change their state. Instead of continually asking, "Are we there yet?" to CLK or DT in a loop, which is very tiring, mind you, we set an interrupt on CLK and DT and then go about our business. As soon as one of them changes state, the interrupt fires and our code can react immediately to handle the event. Once the interrupt executes, the code will resume exactly where it left for the interrupt. It's like setting an alarm to wake you up at 7 a.m. instead of waking up every few minutes to check the time. It's efficient, isn't it? That's the magic of interrupts for you, Explorer. Right. Today, we've got 2 primary tasks to tackle in code. Task 1. We need to read the direction our rotary encoder is spinning, which we'll manage by using a counter of sorts. Consider it our trusty breadcrumb trail to keep track of where we've been. Task 2. We have to ensure our spacecraft doesn't leap like a giddy frog from altitude 0 to 100. Stick with caution. Sudden rises could rip holes in the hull from rocks.
Come on!
Rise too slow, and there might not be enough force to get unstuck from ocean mud. Constant rises could run you into Rachel, the giant whale-like creature hovering around the ship.
Neat.
We need to maintain a steady, controlled ascent, and that means putting safeguards in our code. These are specific stopping points at precise altitudes. We'll use our 7-segment display as our handy altitude meter and adjust our altitude with the rotary encoder. We're not competing in a high-speed race, so there's no rush. Remember the fable of the celestial tortoise and the comet hare? That's right, we're taking a page from the tortoise's book. Slow and steady wins the race. Adjust the altitude, check the display, and ensure the steady ascent of our craft. 1 step at a time, my dear intrepid explorer. Woo! If I had a human voice like you, I think I'd have lost it by now. I think it's time we turn to some instructional material that I've gathered, cached on the computer. I've also added it to your, well, you know the drill.
Okay, all right.
Hello and welcome to day 18. Before we start, did you get the numbers from yesterday?
Yes. Yes, I did. Alright, let's get that. Nope. I don't want to be on that tab. That's the one I'm looking for. Alright, excellent. That's what we fire on cylinders. Excellent. Alright, so we got some new parts here. So interestingly enough, it looks like we did slightly change the wiring of the display to include the breadboard. So it looks like there's actually going to be a little bit of tinkering here from our previous week. But that's okay. So I am going to get us over to the bench, and I'm going to follow along with a fun little diagram. Alright, cool. So we're over there now. And I'm gonna get me over there too. Fancy, I know. Add a little bit of additional lighting. Okay. So we got our wire, and then we've got our friendly breadboard. And then let's see here. I gotta locate us some other stuff and things. I need the rotary encoder. Was that in an anesthetic bag? No, it was not. It's right there. Okay, so we got that. And then let's see, that she mentioned we're only using 2, 3, 4 out of the 5 pins on that. So let's see here. 1, 2, 3, 4, and that's a block of 4, which will allow us to connect the bits and bobs together. And then looks like we have to funnel some voltage here. So it looks like we're tying the 5-volt rail on the ground to the breadboard. Now I know there's more than one ground on here, but I guess there's only one 5-volt rail. So yeah, I guess there is no way to not unplug that, which is fine. Not a big deal. I'm gonna grab myself a wire for the ground and a wire for the 5 volts. So we're gonna take our 5 volts out of there. Oh, wait a minute. Let's get a little closer so we can see what we're doing. Okay, I'll move this out of the way. display in frame. That over. And we're going to scoop this up. That. Okay. Excellent. Alright. So this still needs 5 volts, but that's okay. I'm going to plug this into the port for 5 volts. Excuse me while I look at this because it's on the small side. Okay, so I'll plug that in there. Into there. Potentially. So I'm going to do something slightly different just to make things a tiny bit easier. I'm going to leave the ground that was connected to the display just connected. There's 2 grounds that are back to back here so that I don't have to ground out the display directly to the breadboard. I'm just going to do it directly to the Arduino board, or Hero Bat board as it's described. So I'm going to take my 5 volts, plug it in 5 volts, and then I'm going to take the 5 volts that is for our friend, plug that in there. And then we've got ground, which will attach. So now the breadboard is grounded. And then we've got to grab our rotary encoder. And I'm going to just use our banana style connector. We got the female end on this side, the male end on this side, and just pop them right on. So colors don't necessarily matter here. As long as I plug them into the appropriate place on the other end, it doesn't really matter too much. So for right now, ground is going to be green. The positive 5 volts is going to be yellow. And that's because they're right on top of each other in this little kit. We're going to ignore the switch. And then orange and red will get hooked up to DT and clock respectfully. So then, what we end up having is that. So we're ignoring the switch in the center, and she was right. You can hear it. That click, that's the but you can actually see a little bit of path of travel here. Focus. That's the button that she indicates, and you actually can see that little bit of motion. But our particular example doesn't require that, which is fine. So let's see here. So ground and 5 volts is going to be the green and the yellow. So green is going to go to ground. Yellow is going to go to the 5 volt rail. And then we've got clock and DT. So clock is going to get plugged into 6, and then DT goes into 5. Now the display here is plugged into 2 and 3 on that diagram. Did that change? 2 and 3, 2 and 3. Yes. Okay, so we're reusing a similar component, but we are going to be moving where they're plugged in on the breadboard, which is fine. We're just going to be manoodling some of the stuff around here. So let's see here. Before I plug in the data pins on our little twisty bit, I'm going to have to move clock from where it is into pin 3. So clock on this one is purple. Clock is purple. And DIO is blue. Purple and blue. So purple is going to go to clock, goes to 2. So purple goes to 2, 0, 1, 2. And then the DT goes to 3. So then that moves the display down a little bit. And then we've got our terminals for the twisty bits. And then the clock, which is red in this case, is going to go into 6 on here. So if I've got this correct, 0, 1, 2, 3, 4, 5. Nope, I'm off by 1. That's 7, so then 6 should be there. So 0, 1, 2, 3, 4, 5, and 6. Okay, I should have this all in the appropriate place on the breadboard. Excuse me, the hero board. And then we're all tied into our friendly breadboard. So now, all the action, once I plug it in, is going to happen between that display and this rotary knob. Just like any other week, the code that was on the board previously is still here. So we are going to see our 3 generated numbers from last week, which, as I have written down, because it said we needed them, was 23, 353, and 1688. So I'm going to have that handy with me over here. And then we're going to fire it up and see what we do. So for right now, I'm going to plug it in so that we can program it. So for right now, I'm going to fire up, and we're going to see what we saw from last week. We are not going to see what we saw from last week because I moved the pins. That's right, I forgot. But that's fine. So no harm in this. The old code is pushing out the readings for the display, the rotary knob. As you can tell, the rotary knob does not have a display. So obviously right now it's not doing anything, but that's fine. This component isn't going to be bothered by some pulsing signals. It's an input, or excuse, yeah, it's an input, not an output. So right now the knob isn't doing anything, but the component's not bothered. It doesn't care. Not until we get that code in there. I totally forgot. I literally just moved the pins too. Oh, that's great. Naturally, right? That's interesting. Why are my shoulders twisted? Hello? Give me 1 second. I am really looking. I'm looking good here. Oh yeah. That's better. All right, cool. All right. Now that we got that into gear here, let us get a new project open. We're on day 18. Okay. I don't know if we'll need the serial monitors. I'm not going to worry too much about that right this minute. Oh, before I do anything else, hang on. Let me actually just upload this blank sketch real quick. Okay, cool. That clears out all the previous code from the previous example, which gets us back in business. Okay. Yeah, let's see what we're working with here. All right, so let's see. So the comments say it's time to examine how we can control our lander's ascent from our watery depths. For this, we'll use a new device from our repair kit, the rotary encoder. We will turn this dial to raise or relower, our lander from its current resting spot on the seafloor. Of course, we can't risk any unauthorized use of the control, so you will first need to enter the 3 numeric keys from day 17 into the keys array below. If the correct keys are entered, then the controls will remain locked. The rotary encoder allows us to detect when the dial is rotated and track which direction and how far. The rotary encoder can also be pressed down like a button, though we won't be using the function in this sketch as we saw in the example. Alright, so we have some stuff here that's commented out in the top. Arduino concepts, introduction documentation in this lesson. Interrupts. Okay, so real quick, when I was working on the big red button that we used from one of the previous exercises, I had always wondered, I didn't take the time to expand or explore on this concept, but if I click that button and I had it in the main loop, well, then we needed to wait until the loop came back around to check to see if the button was clicked. Just like she had mentioned during this example that we're getting into tonight, is the fact that you may want to stop the code in its tracks to do something, an interrupt, which is fantastic because I was kind of hoping there was a capability to do that, because in a perfect world, I would have used an interrupt to detect the big red button getting clicked during the creative day 15. But I didn't know about it. Now I know about it. So I think that's going to be really interesting to see kind of how that plays out and how the way that the code flows with that. I don't know. I'm excited. Very excited. So we got that attach interrupt function that allows us to configure a function that is executed when an input pin's value changes. Digital pin to interrupt converts a pin number to an internal hero interrupt number. Note, the hero board only supports interrupts on pins 2 and 3. Interesting. Okay. Parts of electronics concepts are introduced in this lesson. Yeah, we know about that. Okay. All right, so we're off to a roaring start. We have got our explicit include for a couple different things here. So above our void setup, we're going to have our include for the Arduino, which allows us to use the pins that are configurable on this board. Without the Arduino library, nothing will work. That's been true every day that we've done one of these. It's going to continue to be true moving forward. We then have the included library to control the display. This one we're also reusing from the previous week. And then we've got the basic encoder library. So this is going to be the library that allows us to use that new fancy Spiny Bit that we've got from the kit. Okay, let's see what we're doing here. This is also another thing we're doing above the void setup. This is code that is only run once when the board turns on, because it's above setup. Controls will be locked unless the correct keys from day 17 are added here. Replace 0 with the first key, 0 with the second key, 0 with the third key. Okay. So we already know we have this. But before I change it, I want to bring the code over. I want to try it before we put our numbers in, because I have our numbers. But I want to see what happens when we don't have the right numbers. So I'm just going to leave that alone for the immediate future right now. We'll come back to it though when we go to run it. Part of me is kind of happy they didn't re-involve the keypad on top of all of this. That would have used a lot of pins. Okay. Alright, so the rotary encoder will be used to control our landing. Yes, we know that. The hero board supports only interrupts on pins 2 and 3. We must use those pins for rotary encoder input. Rotary encoder inputs. Depth control, clock pin 2, depth control pin 3. That makes a lot of sense as to why we moved our display. Our display was down in that position, but we can't interrupt the code if those two interrupts were connected to a display. Because there's no way for us to interact with the display that would activate an interrupt. So of course we moved it. That makes sense. To which then we just declare those two pins, which is totally fine. Let's see here. We're going to do a couple other things. Okay, let's see here. So then now we're going to create the object for controlling the encoder. So we call on the class that is inside the library, basic encoder. Depth underscore control is the name of our object. So anytime we want to interact with the rotary knob to either read a value, positioning, whether the switch was clicked, which isn't connected, we would interact with the name of this object, depth underscore control. And then we then pass it where the pins are connected. So clock pin and DT pin, which are on pins 1 and 2, or excuse me, 2 and 3, which we have declared right here. Okay, so then we're gonna nab our stuff here for our display. Okay, so then we do the same kind of thing. We call on the class of the TM1637 display, which we are pulling from the library we imported. Depth underscore gauge is the name of our display that we're going to reuse anytime we want to do something with the display. That's the name we're going to call upon, because that's our object that we have made from the library. So a little bit about the idea of what that even means, right? So if I have a book, right, on a shelf, and inside that book we have the way to do a specific thing, right? I can make a copy of that construct and slap a label on it and say, this is my display. Everything inside this container that I then interact with is just a copy of what was in the book. And I could make as many copies as I want. I could have multiple displays hooked up. And every time I want to interact with one of those displays, I then just use my friendly name, which is the name of the object we created, to just refer to that display, or to refer to that object. If you have 3 bananas on the table and you have them named banana 1, banana 2, and banana 0 because you're evil like that, you know the difference between the 3 of them based on their display name. And you can interact with all the classes and everything that's capable with a banana, like peeling said banana, or if you were chopping up said banana, so on and so forth. Same kind of thing happens with computer logic. If you call upon a class, that class allows you to do whatever is defined within it, which makes your code a lot shorter, but if you don't read through the class, you don't know what it does. This is a guided example. So I know that the display, at a minimum, needs to be told what things it's connected to so that we can control it. If this object declaration, where I say slap the name on the container, required more information for me to actually use it, well, then I would need to read up on what the library requires. So no, not all this stuff is self-explanatory, but everything that is here is very well documented, which gives you the ability to all right, hold on a minute. That threw me so bad. We're gonna switch down. There we go. Okay. It's one thing to be talking about technology and a guy going, yeah, yeah, in the background. I'm like, okay, I know you're listening, but try to stay with me. Oh, the background music can kill a brother. Okay, moving on. All right, what do we got here? Constant byte blink count 3. Blink depth gauge this many times for attention. Dad! Like, what? Yes, that is that. It's going to be our bugger to get attention. Lovely. Depth gauge pins. I think I copied this more than once, didn't I? Did I copy that more than once? Pins 2 and 3. Oh no, I did not. Define the display connection pins. Why the heck did I declare it down here? Wait, was it like that in the example when I copied it? Or did I copy this out? I copied this out of order. Yep, that makes sense. You declare it before you use it. These belong above that. That goes up here. It's far from done, but did I... Ooh, okay. I'm gonna have to import that library, but that's okay. With the basic encoder. Not a problem. That's a simple one to fix. As a matter of fact, was that mentioned up here? Is it down here? There it is. Haha! Yeah, we're gonna need that. Okay, so we got that. And then we're gonna go to... manage libraries. Actually, do I do that from here? I don't need to import that into this project. Include library, add zip library. Yes. So what we got was an error indicating that the library wasn't available because I called upon something that wasn't installed. So now that it's installed, by downloading it, this will now verify. Tedious. I'm sure they would have mentioned that in the example, but I didn't play the example because I am the example. I'm making an example of myself. All right, let me get us back up into action here. Okay. So now we're gonna grab a section. And this looks like it's all still above the initial setup, right? Yep. Void loop is right there. Oh, there's void setup. Okay, so yeah, we're not quite there just yet. We're almost there though. Okay, so next thing we're gonna do here, it says you can set the individual segments per digit to display words or symbols, so on and so forth. Right, so as we had seen before in the past, there is an ability to control the individual segments, and by passing these segments for all 4 segments of the display, we can spell stuff. So for the letter D, we have to turn on segments B, C, D, E, and G. And then for O, so on and so forth. So that allows us to call upon a variable that's in the size of a byte that would spell out done or nope. Those are the 2 words. And to pass all these segments to the display to make them light up, we would just call upon this array of segments that are either on or off. So that's a one-time thing that happens before the initial setup. And we have a couple more items here that we gotta pull over. Okay. So that is going to be... our lander is currently this deep underwater, so this is what's initially shown at our depth gauge. 4 digits, 7 segment display. We have initial depth of -60. Alert the user when we rise above these depths. We've got alert on depth 1, 2, and the surface. So depth number 1, first alert, is at -40, which means we're starting to rise. -20 means we're pretty close to the surface, and then 0 means you are at sea level. Makes reasonable sense, and these are just 3 individual variables, integer variables, that we have supplied meaning to. Okay. So let's see here. So our void setup. I do not understand why it does that. Out of curiosity. I switch hands. interesting. This one must have a bad camera on the right-hand side. That's terrible. Ugh. Because there's no other reason it should be doing that. If it loses tracking, it's supposed to just go back to normal. Alright, let's grab our stuff here for the initial setup. So this is code that is also only run once. Okay, so since we have some action going on here with the serial monitor, we have to call upon it. So we're going to start the serial monitor, which means I need to show the serial monitor. So we're going to be seeing stuff on the screen here. We're going to set our brightness of our gauge. Maximum brightness is 7, so it's between 0 and 7. So boom, maximum power. Let's see here. Keys are valid. Oh, okay, so this is going to call upon our 3 keys that we have from the previous week. And then the depth gauge, if that's true, it will show our initial depth, which is -60. Otherwise, the depth gauge will show nope on the display. And then print invalid keys. Please enter the 3 keys from day 17 in order in the keys array at the start of this sketch while true. Now what I find interesting here is that if keys are valid, which means our keys are right here, so that's going to pass that to this function that we haven't written yet. We don't have it in the code yet. And it's going to verify them. So I am interested to see what they did to prevent you from just looking at the keys verified function to confirm you have the right 3 numbers. I'm going to be curious to see it's going to compile, right? But they're probably going to have this obscurified in some fashion. Obscurification is not encryption. Obscurification means that you take something and you make it hard to understand or hard to follow intentionally, so that it's not easy to understand the intention of the code. That concept can appear in many places in life. Sometimes that's done to keep information from being misinterpreted. But nor here nor there. That's something that's going to happen in this example. So it's going to call upon that function, and then as long as it's true, we're going to kick off to the main loop, which I'm curious to see what the code does if that's not true. So let's see what our action is here. Our hero board allows executing code to be interrupted when the value of a pin changes. These 2 commands allow us to provide code that is executed whenever the level of a configured pin is changed, as occurs when the rotary encoder is turned, because we have them plugged into 2 and 3. When the rotary encoder is turned in either direction, our update encoder function will be executed. When update encoder completes, the code resumes at exactly the place where it was interrupted. Call interrupt service routine is an ISR when any high or low change, which means we rotate one direction or the other. Attach interrupt, digital pin to interrupt. We're setting 2 of them. So we're saying that if the control clock or the DT pin change, then pump the brakes. It's time to get off. That's what we're going to do. So that we're going to bring over. That's the last thing in our setup section, by the way. That's not in the main loop. That is the last section of right here. Just gonna verify this one more time to make sure I didn't do a boo-boo. Oh, okay. I didn't do a boo-boo. I haven't declared this function yet. That's gonna come later. Further down but actually it's probably gonna go underneath the main loop. Yeah, I anticipate that, Red. That's completely expected because I'm trying to run a function that isn't declared anywhere. I couldn't get into a vehicle and drive away if I didn't know where it was. It's literally the same exact thing is happening here. Very important to know where your vehicle is before trying to get into it. Otherwise, you could be driving the invisible boatmobile. I hear the paint job is incredibly expensive on that vehicle. Okay, so we're going to enter our main loop here. And let us see what we're doing here. So it says if the depth control dot get change. So if the depth control value has changed since last check, the rotary encoder library always sets the initial counter to a 0. So we always add our initial depth to the counter to properly track our current depth. Interesting. I was wondering about that because since this encoder doesn't have a beginning or ending position, technically the dial could be in any position. How would you know where 0 is? Each time it resets, by the way, this library is written, it resets it to 0. Now understand something. I am reusing a library, which makes it easier to interact with the component without needing to write each tiny detail that makes it function. If I used a different library written by a different person, that might not still be true. So if I got a different library on using one of these encoders, it could very well mean that when I go to turn the knob, that starts at a different number, something other than 0. So it's good that we have that notated, and if it wasn't in the comments very readily here, I wouldn't have known that, which it would have required me to look into the library to hopefully have a better explanation as to what do, you know? So then we get our current depth is an integer that starts with our initial depth, which starts at -60, and then we add whatever we read from the dial. We cannot go deeper than the sea floor where the lander sits, so reset the counter if the user tries to go deeper than the initial depth. Listen, I'm not saying we're not going to go digging, okay? But I feel like we probably could with this spaceship. Which makes sense. Yeah, if we go below the initial depth, then we reset it, which that's fair. Now, interestingly enough here, depth underscore control is dot reset. So reset puts us back where we were. Now we said the current depth is equal to the initial depth, which we do have declared up above. Did we initial depth? Did we pass that to this function at some point? We set it right there. I have to admit, I don't quite understand why we'd be calling this dot reset. I don't know, maybe it'll make sense once we put the rest of the code in here. Because I would think just doing this, saying the current depth equal to the initial depth, it resets it. What on earth is that for? I don't know. Okay. So we're going to run through that. And then, once we've stopped rotating, the code continues, right? To which then the code is going to pick up where it left off. And then it's going to call upon our depth gauge, which is our display, right? So we called it the gauge, which is what it is at this point, right? And then we're going to show the number in decimal of the current depth. So if we rotate it past -60, it'll just say -60. If we rotated it in the positive direction, or clockwise, I think, actually, we're going to see the number start to rise. And then to give us an opportunity to see it, we have a hard-coded delay in here of 50 milliseconds. So that's going to be fairly quick, but that's going to give us an opportunity to see the number on the display. All right, let's see what else. We got a lot of comments in this example this week. Since basic encoder can be clicked multiple times per loop via interrupts, we track when counter has passed milestones, this time through the loop. We do by testing whether the previous counter was less than the milestone and current counter is greater or equal. Explorer, to prevent stress on our lander, we should not rise too rapidly. To keep you alert, we will blink our depth gauge when our depth goes past predefined levels. Because the rotary encoder might be rotated more than one click between loops, we'll write our code so that we can detect when one of our warning levels has been reached or passed. We do this by tracking the depth reached by the previous loop execution, and then comparing this to our current depth to see if we cross one of our warning levels. Depth from the previous loop initialized to our initial depth first time through the loop. Okay, so we're giving the loop an ability to keep track of what on earth we've been up to, which is fair. So we are going to create a variable called previous depth and not set it to anything. And we got a couple of other items here I'll wander on over. Okay, so if we crossed our first alert level, then blink our depth to alert our explorer. If the previous depth is less than the alert depth and the current depth is greater than or equal to the alert depth, blink the current depth. So if the previous depth is, well, nothing because we didn't set it to anything, and the current depth, which would be -60, is greater than or equal to alert depth number 1, which is -40, then we are going to call upon the function called blink depth and then pass it the number of our actual depth. So this should not only cause a number to appear on the screen, but for it to blink the number on the screen according to this helpful name of the function, which again, we haven't written yet. We still need to. We're still calling it, again, we're calling it a function that we don't have in the code yet, but since it's been given an incredibly helpful name, that gives us a pretty decent idea of what to expect. And then we're going to check basically for the same thing again, except if we're at the alert depth of the second check, which was at -20, which means we're pretty close to the surface, but we haven't breached quite just yet. Okay, so then after we've checked for those, if we've crossed our second level, then blink our current depth to the explorer. Oh, I read that already. We've reached the surface, blink done on our depth gauge if the current depth is greater than or equal to the surface depth. Well, let me tell you something, folks. If we're above sea level, that means we're floating above the water, which if we're in a spaceship, hopefully that's what we call ideal. So I'm a little surprised that it didn't reset it, which is funny. If you go to quote unquote high, there is no too high, there's just too low. But I don't know, man, I feel like this thing could dig. Fancy ships. Let's see here. We do fall into a for loop. And then our blink count, what are we doing here? Oh, there's systems for a too high. You know, that's a very fair point. So So we can see here, so if an integer I, well, I is less than the blink count. Now blink count was 3. We declared that up top. The depth gauge is cleared. We delay for 300 milliseconds and then display the word done and then delay again. So that is going to cycle 3 times to blink done, 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 with a pause in between. The previous depth is then set equal to the current depth. Save the current depth for the next time through the loop. Now if we look here, that is the curly brace of the void loop. This is an extra one. I don't know where I brought that one over from. Yeah, I think that's right. I had an extra one. Which again, I know I haven't written the functions yet, but I shouldn't have an extra curly brace, or at least I don't think I do. Oh, that semicolon actually belongs on this line. Function define is not allowed here before token. What line is that on? I might have needed that after all. Well, we'll pull over what I see here. We'll go from there. I nuked it. That was the one I took out. Got ya. Oh no, that actually was required. What brace is that to? I'm not worried about it. We'll keep going. I know once I declare the functions, if I'm missing a curly brace, it should stand out. Okay. So then, outside of the main loop, which should be out here, remember I mentioned that code was going to be obscurified? Yeah, here we are. So, are the keys valid? Unsigned integer I is equal to 0155. And then, what on earth are we doing to this? Key 0 is not equal to this plus whatever that is. And then I plus equal to. So yeah, it definitely does some funky math there. And then if key 2 and 1 return this fairly cryptic looking statement. Return not that. So if it's not that, otherwise return that gobbledygook, which is going to tell it to proceed in some capacity. I was curious to see how they obscurified that. I'm sure this could be picked apart. I just don't have a reason to. Definitely looks ugly. I figured it was probably going to look ugly, but that is easy enough to just prevent you from coming over here and looking at that part of the example and going, nope, I'll figure it out myself. Alright, yeah, I'm getting there. We haven't gotten there yet either. Okay, so then we're going to blink our current depth. So the blink depth function, which we are now adding, we're going to take an integer of the depth, and then we just blink it, looks like 3 times. Right, the blink counter is at the top, that's still a 3, which is fine. We're going to clear the depth gauge, which is going to clear the display. So if there's any numbers on it, it's going to move them off, right? We're going to pause. We're then going to display the number, delay again, and that's going to cause it to blink because the loop's going to run 3 times. It's going to blink, boom, 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 with the pauses in between, and then keep on rolling. And we have a couple more tidbits here. This is our interrupt handler function that we configured in setup. Whenever the rotary encoder pins change, we call the service function from the basic encoder library, which handles all of the calculations to track the turning of the dial and update a counter, which we read in the loop. Okay. So that's interesting. So I actually want to compare this code to the other item there. Okay, so I did accidentally nix something important here. A function definition is not allowed here before the open brace. Oh, that means that has to go down here, I think. Nope, didn't like that. That's what I get for pulling this over in chunks. I sometimes will do that, where I either grab an extra brace because I copy it more than once. Right, so the void loop, it thinks, closes right there. Which then... That's that one, that's that one. That one closes there, that one closes there. And you think you close down there. Which would make that an extra one. Which means I nixed one right there. Oh, there it is. I knew it was in there somewhere. The curly brace is the world champion of hide and seek. You'll find every coder everywhere always playing a cat and mouse game of where did the last curly brace run off to. Wouldn't be the first time I've gone on a hunt. Certainly won't be the last, especially with me doing what I'm doing now. Needless to say, it's always a good time. Okay, so we need to turn on the serial monitor because we want to see stuff. So I gotta find that. These are tools. Tools, serial monitor of the cereal variety. Great breakfast cereal. Fun to play with, not to eat. If you're eating a cereal monitor, we've got bigger problems. So I want to take a look back up. We're going to scoot back up here into before, I think that was before the initial setup. So these are our keys. I didn't forget about this. I'm amazed I didn't forget about this, that I didn't put in our keys yet. So when we run this should just straight up basically tell us to go away. And then it doesn't work. Now, if we look at the completed code here, we've got our declarations for done and nope, our initial depth values. Here are our 2 interrupts that we have. We have in the void setup, digital pin to interrupt. So if the depth control clock pin or the control DP pin change, update encoder. So update encoder passes to that name of that function. And then change is the thing that we're looking for. Macro change. Define change. 1. So, all right. So I'm the capacity of something. If something's different, then run with it, right? So we're looking at that pin. So update encoder, which we do have the bottom here, right? Yeah, update encoder is this void function. So depth underscore control dot service. Service is a void. To update the encoder, changes call this method in a timer interrupt for best performance. It could also be called in main loop. This takes about 10 to 15, I think that's microseconds for US, using digital read on an Arduino Nano. But we're doing it from an interrupt. It makes sense that you could still call and read the dial without the interrupt, but as long as you have the pins and the capability to, I don't really see why you wouldn't. And then the code picks up where it left off. So depth control dot get change, right? So if we come down here, depth control is the variable that holds the information, right? So when we turn the knob, it's going to cause a trigger to update the value. And if I'm reading this correctly, by calling service, service is going to update what that positional change is from 0 into the depth control, which then at the top of our function, if I'm reading this right, we then ask depth control, okay, you just made me stop what I was doing. What was the change? To which then we look at our initial depth and add on the positive or negative value that makes up our change in depth. Which then from there, we're going to see some stuff. We're going to get some blinks. So I think we've pretty much picked this apart about as well as we're going to. I'm going to verify it one more time. And as long as I put everything where it belongs, we're going to upload this to the board and we should see some action here. Which is exciting. All right, so we're uploading. Okay, so as expected, I did not put the keys into the code. I have them written on the sticky note, and we can see error, invalid keys. Press enter. Please enter the 3 numeric keys from day 17 in order in the keys array to start the sketch, right? So it straight up tells us right now that we don't have everything we need because I didn't put it in the code, right? Now, if we take a quick look at our display right now on the bench, we see nothing. So I was curious to see if we didn't provide those unlocking keys to this example, would anything happen? And interestingly enough, no, we get nothing on the display, which is interesting because at no point did I tell this to not go into the void loop. Interesting. Because I know we go through the void setup here. Oh, that's what holds it hostage. Right there. I just realized that. This if statement actually stops the code from proceeding. A reason being is that if the initial depth, or excuse me, if the keys weren't valid, then this else statement grabs us, and this chunk of code literally keeps us hostage until the right values are inserted. Because right there, it's a while true loop. So it's going to keep it there until we give it what it wants. Which, yeah, while true. Where's the other half of that? That's a part of this. Else, while true. So then the code just doesn't proceed forward. I was wondering wondering about that. So all right, cool. So now that I got to see it do nothing, and you guys got to see it do nothing, let's make it do something. So let's put in here our numbers. So we got 23, 353, and 1688. Okay. So we're going to compile that, make sure it's happy. Okay, so I'm going to clear the terminal. Upload it. Hopefully I got the right numbers written down. Okay. Well, there is no error to our terminal. So that's fun. I'm half wondering if I don't think, does the terminal even do anything else in this example? I don't think it does. So the fact that we didn't get an error should mean we're good? Question mark? I think. Well, that's really frustrating. And if you could stop losing tracking, that'd be fantastic. Yeah, serial begin, there's the delay. And then we go into our depth. So if we take a look at the camera right now, there's nothing on the display, which could potentially mean it plugs things in where they belong, which is fair. I might not have. Let me take a quick peek at the code here. So code should be running right now because we gave it the decryption keys. Which then, if the depth control dot get changed. So we haven't turned anything yet, right? So that wouldn't have run. Let me click upload again. I want to see if it just quickly flashes on the display. Our depth. Interestingly, no. We see nothing on the display. No number digit. Previous depth. We declare it, but we don't do anything with it. Okay, so looking at the code, doesn't look like there's anything to actually cause something to appear on the display until we interact with the knob. Let's do that. First things first, I'm going to ground myself. Okay, if I have this hooked up correctly, clicking the switch does nothing as I anticipated. And I'm rotating and I've got nothing, which means I probably don't have something hooked up correctly. But that's okay. Let me take a look at our diagram again. And let me verify the wiring. Because I probably made a boo-boo and didn't plug in something where it belongs. Which is fair. So let me see here. The rotary six and 5 is where the display goes. Okay, so I plugged them in backwards. I plugged the display in where the rotary knob was supposed to go, and I put the rotary knob. Yeah, I did it backwards. So give me a moment while I disconnect this from power and put these where they belong. Alright, so our friend here, we're supposed to be in 2 and 3, and I read that with the greatest of ease. So I'm going to disconnect those two, and then our friend clock is supposed to be in pin 2. 0, 1, and 2. And then our lovely clock clock, which is the purple one, is supposed to be in 6. Okay, so as I had mentioned, I had them in backwards, so I just switched the location of these respectfully to where they actually go. So now, without further ado, something should happen on that display when I plug this in. Because it should have, yep, there it is. That's better. That's what I was expecting it to do. Looking at this, it was supposed to display our depth, which works a lot better if the display is hooked up to the appropriate pins. Yes, as one can only imagine. Okay, so now, we're gonna have some fun. Now we got some stuff here. I'm just gonna check quick. Clicking should do nothing. Actively doing nothing, which is good. I didn't expect it to do anything. Real quick, I'm gonna look in the serial monitor, and there's still nothing. Okay, so with everything plugged in correctly, there's nothing in the monitor. It's just a white terminal. So I'm gonna spin this. We're gonna go clockwise. Boop, 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 boop. I give it 3 clicks. Now there's potential. I still might not have it where it belongs. Interesting. Okay, so if I go really slow, it doesn't always register. Or wait, I can't go below 60, that's right. Alright, so I can actually feel the clicks in this. And it's every other click on the knob, I see it move. So that's 1, that's 2, that's a depth change. 1, 2, that's a depth change. Same thing with the reverse direction. 1 click, 2, depth change. 1 click, 2, depth change. So now, we're gonna start going back to the surface. We should see some action happen here once we go above 40. There's 40. That's interesting. So it said we cleared the threshold. What if I go back down? No blink. I spun that really fast that time. Spin fast again. There's 20. And there's nothing all the way up until done. 3, 2, 1. Done. If I don't touch it, I'm wondering if it disappears. I don't think it does. That's fun. We're going away. We're sinking back to the bottom. What if I just spin this endlessly? I know we've got the hard stops, right? But if I keep going. Yep. Okay, so I actually can speed past those other positions if I go really fast with the knob. Which, yeah, there we go. Put me over there. Oh, that's right, because I'm still climbing. And I'll keep climbing. Oh, if I spin this way. I can keep climbing past done. And I'll very briefly see that number of where we're at. We're at 174 above sea level. And it'll keep flashing that as I start to descend this again. There's 80, 70, 37, 7, -1. That's really fascinating. Which makes sense, because that's actually exactly the way the code was laid out. I can't go lower than sea level, which is lame. I totally want to go lower than sea level. Just to say that I did. But it won't let me. Because that's the way the code's written. Which is awfully exciting. I thought that was awfully neat. What do y'all think? What do y'all think about that complete shenanigan for what it's worth? That's awfully interesting. The interrupt makes sense though, because that gives you the capability to stop the code, do something else, and then just keep going. which for an interrupt that you would require to hit the brakes, like, hold it up here for a second, I need to do something else first. All right, now proceed to continue what you were doing. That makes me think even more about that button I made. That makes perfect sense. At any point, if I hit the panic button, big red button, I would want the code to stop what it's doing, lock out the terminal for a defined amount of time. Now, the thing that was different between me and this code, though, is that I would probably not want it to pick back up where it left off. I would want the code to restart in some capacity, right? From the beginning. So I'll be curious to see if we run across anything that prevents the code, that could force the code on an interrupt to start back to the beginning of the loop and start over. The way this one's written, it just picks up where it left off. So I'll be curious to see if it gives us anything like that. And if it doesn't, probably going to want to look that up, because I find fairly fascinating that you can actually pump the brakes on that and then continue as if nothing had happened. Which is great, because that gives us a capability to grab that information and then keep going. Which is why you notice the done flashing rapidly on the display, because we had quite literally pumped the brakes to see what we were up to, gather that value change, and then keep going. We saw the reflected difference because we just added that negative or positive number to our running tab. Because again, it always shows that spin of that little dial starting from 0. So we're either adding or we're subtracting from our running total, which is fair. I find that awfully interesting. Huh. You know, I wasn't really sure how the rotary dial worked, because I did notice that in the kit when I first opened it. Naturally, I did take a little time to like wander through what was in the kit, and it definitely seemed like something that could be potentially difficult to use, but it actually wasn't too bad. But since it doesn't remember state, that actually makes a lot of sense that you just snap that value. That's cool. That was very cool. Gives us an opportunity to learn something along the way, which is awfully nice. With that, let me see who's on. Lots of beans on.